So remember, I want to discuss the lab reports, the first ones with each group, right? So make an appointment, we'll find some time, right? Let's do this week. So yesterday it took a long time, a lot of development, but we finally established conservation of mechanical energy. So and what that is in an isolated system, the mechanical energy, isolated meaning no external influences, no forces from the outside, the total energy is constant. It can be transferred from one form to another, kinetic potential or kinetic energy of one mass to the kinetic energy of another mass, but the total energy has to be a constant. And I want to point, before we go further, I want to point something out here. Remember, we got this, we used the work kinetic energy theorem. Whoops. The work kinetic energy theorem. And here, we've been doing this all along. This is the work done by the net force. And we don't think of that force as being part of the system. That's some external force. We think of the body, one or more bodies, as the system. Right? And this force is from the outside. Well, once we do this, something's happened here. For a conservative force, the work done by the net force is going to be minus the change in potential energy, as we discussed yesterday. So when we have a potential energy, we can substitute for the net work here, minus the change in potential energy. And then I made a big deal out of bringing this over to the other side, which seems like a trivial mathematical step, but it really represents a shift of perspective. Because now, what is our system here? When we say that the total, let's take free fall as an example. Energy is conserved in my system here, right? I release this from rest. We initially have some potential energy. Let's say we measure from the floor, mgh, measure from the floor. We can choose any reference we want. We just got to stick with it. And energy is going from potential energy to kinetic energy. What's our system here? What's the system? The system actually includes the Earth now, because the potential energy is part of the system and the Earth is responsible for the potential energy. So we actually have an isolated system here. We've now included the Earth. So there's a fundamental change in perspective here. And it makes solving problems a lot easier, in a sense, okay? As long as usually we care, you'll see this today, we care about often we care about an initial state and some final state. And we really don't care what's going on in between, and we don't care about the time it takes. If that's true, then you want to use energy conservation, as you'll see. But it won't give you everything. It won't give you all the answers you may need. You may have to go back to dynamics and solve Newton's second law, okay? So we did, I'm sorry I didn't mention this yesterday, but this demonstration with that heavy cast iron ball, demonstration like that is called, it has a name, it's called the faith in physics demonstration. So the idea is if you have faith in physics, you shouldn't have to flinch, right? It can't go higher. You release the ball from rest. We released it from rest here. It swings out, comes back. It can't come back any higher, because that would mean that when we released it, there was some potential energy, right? If it comes back and it's higher in the Earth's gravitational field, that means it had gained potential energy. But it's a closed system. If anything, it's going to lose some energy, right? We talked about the losses here. So that's called the faith in physics demonstration. Here's a smaller, less dramatic version. Okay? So here's our pendulum, and I'm going to release it from rest at the same elevation as this aluminum rod here. So what's it going to do? When it how far is it going to go here before it turn? Where is it going to go right when it's turning around?
It's going right up to the pole.
Same height, right? So at that moment, potential energy, gravitational potential energy is being transferred to kinetic energy. Here it's being transferred back, and finally at the turning point here, we should be right where same height as we got before. So see if that's true. And then when it comes back, similarly, it should go to the same height, neglecting losses. And let's see what happens. I'm going to try to release this at rest, right at the height here. Now I can't see it, but maybe you can see it. So it should be going to approximately the same height, and it's going to be losing a little bit of energy. Well, it's not losing much energy, is it? But I think you can see that the amplitude gone down? Mm-hmm. The maximum, yeah, okay. This is, the faith in physics is dramatic, you know, and this is not really that interesting. In fact, if you just ask people, you know, what's going to happen here, somebody who doesn't know anything about the conservation of energy, I think they're going to tell you that, oh yeah, it's going to go to the same height and it's going to come back. It just seems kind of obvious, right? It's sort of like by symmetry. The symmetry here is actually time reversibility. What the motion starting here and going down to here, this motion here is really just just like you took a movie of this and you ran it backwards. Take a movie of this going from here to here and run it backwards. It's going to go up here and momentarily come to rest. So I don't think it's really that interesting, but we can make it interesting. Now what do we have? Some bent rod. This actually has a name. It's called an interrupted pendulum. So now what's going to happen? I'm going to release it from rest at this height, the height of right at the middle of the aluminum rod. It's going to come down, and now something happens, right? So how far is it going to go on the other side by energy conservation? The same height, right? It should rise right to the height of the aluminum rod here. Because we start, if energy is conserved here, and there's, you know, the losses are small. Oh, and you may be worrying about some losses here. They're small, as you will see. We start off, we have no kinetic energy. There's some potential energy. We can measure it from the tabletop. So it's mgh. Here it's gaining kinetic energy. At the turning point, there's no kinetic energy. It's all potential energy. And it has to equal the initial potential energy, so it has to be the same height. So let's see if that's true. So I'm going to release it from rest here. So can you see it? I can't see it from my perspective here. Does it go to the same height? Yeah.
A little bit higher, it looks like.
A little bit higher?
That's what it looks like.
Okay, let's patent time. Let's file a patent.
Okay.
Yeah. So if that's true, we can make it's called kind of an engine out of it. We can get energy out. We've got an endless source of energy, right? We're getting out more than we put in. Yeah. Historically, that's called the perpetual motion machine. And many people have tried to have come up with ideas, but here's another example. So this is an asymmetric situation. That's what makes this more interesting when I put this rod here. It's asymmetric, and you guys it seems like you had to think about what height, or maybe it's just early in the morning, I don't know. But here's another asymmetric situation. Okay, now this is at the same height. I'm going to release it from rest. Where's the turning point? Where should it be? Right at the same height. It should be right there. And when it comes back, it should come back, assuming no losses, it should come back here, right? So you'll notice it. This is kind of curious. It does go pretty much to the same height. There's a little bit of losses, right? The losses here are probably this rolling friction here. But it definitely, by the time it's come back, it's lost some energy, because you can see that it doesn't quite make it, right? Okay, any questions about? We'll come back and we'll do another demonstration with us towards the end of the lecture. Okay, any questions or comments? All right, so now what we want to do, now it's time this really helps having this this subject here, this information, sink in as we do problems, right? So we're going to do a bunch of problems, and we'll do homework problems too, of course. So let's first of all look at a roller coaster. We'll assume we have a mass here that's sliding without friction on some kind of arbitrarily curved ramp here. And we release it from rest at the top at a height 8 from the ground level here, some height h, and we want to find the final speed, the final velocity. So is the acceleration constant here? No, it would be hard to find the acceleration here because it's going to depend upon, if it's a straight ramp, it's constant acceleration. Straight ramp with a little rounded section there, it's going to be constant acceleration down the ramp. We could use Newton's laws. But this is not straight, it's curved. So you'd have trouble using Newton's laws. And you might have to probably shove it on a computer to do it. It depends on the nature of the curve here. But with energy conservation, we can easily do this problem. And you'll note that we've got an initial state and a final state, and we're not worried how long it takes to get to the bottom. If you want to find out how long it takes to get there, Newton's laws, and with a computer probably. Now, first, note the normal force. There is a normal force here, but it's doing no work, so we don't care. It does no work. It doesn't enter into the energy conservation. We just have gravity and kinetic energy. Right? So, here's the idea. The total energy is the kinetic energy plus the potential energy. Kinetic energy is 1/2 mv squared. The potential energy, this is constant gravitational field, constant gravitational force. So the potential energy is mgy, where y is positive upward. The greater something, the higher something goes, the more potential energy it has. So that's why this is right. If you chose y to be positive downward, you'd have to put a minus sign there. So you need to be careful about that. But you can do that, you just need to be careful. So here's the idea. The energy's constant. So what's the initial energy? It's all potential because it's released from rest, so it's mgh. The final energy, we're down here where we have 0, that's our reference level, there's no potential energy. And these two things have to be equal by energy conservation. Now, I want to make sure you understand something. The energy is conserved all the way down here. We could take an arbitrary point between here and the final state, and energy will be conserved. And you can use that to gain information out of the system. But ultimately, if you want to know what this thing is doing as a function of time, you're going to have to integrate. You're essentially using Newton's second law. You can use the energy, but in the end, to get that detailed information, you're going to find that you're integrating, you're doing Newton's second law, integrating it. So it's that easy. The initial energy has to equal the final energy. Here's the initial energy, it's all potential. Final energy is all kinetic. We simplify, cancel the massless, and we get the square root of 2gh. Now that expression will look familiar to you, and I'll talk about that just a little later. But let's continue with our understanding this here. You'll notice, how does this answer depend upon the path, the particular path?
It doesn't.
All it depends upon is the change in height, right? So if I had this dotted, suppose I had the dotted curve here, what's the final velocity going to be? Square root of 2gh. It'll be the same. And here's something interesting. What if it comes down like this and then goes up and then comes back down? What's the final answer? Yeah, but we have to qualify that. Here, let me give you a hint. Suppose it comes down like this and goes up here and comes down. I've heard a lot of talking, but I couldn't discern any.
It never makes it down to y equals 0.
That's right. We'll talk about that. We'll solve a problem later on today. We'll look at that. So when we say, this is, I guess, technically not correct here, and I'll fix this, when I say that it's independent of the path, there's a qualification here. If there's a hump here, a positive hump rather than sort of a negative hump here, it's got to have enough energy to make it over that hump. If it doesn't, it's just going to come back. But at least for this path, it's going to have the same final velocity. Doesn't depend upon the details of the path. Now, I know some of you are feeling funny about this, so I think it's worthwhile here. This reference level, okay? You can choose this to be anywhere. You just have to stick with it. I've told you that a number of times. Let's see it in this case. Let's choose our reference level. Let's choose the y origin to be at the top here. That's fine. We better get the same answer, because believe me, this roller coaster here doesn't care what we think, right? So, how would we do the problem if we chose the origin to be there?
What, the y negative.
So what's the energy is conserved? What's the initial energy?
U equals negative mgy.
No.
Or
We have no kinetic energy. What's the initial potential energy?
mgh. 0.
Thank you, 0. If we chose this as our origin, we're going to call y is equal to 0. Instead of calling this y equals 0, we're going to call that y is equal to 0. And there's nothing wrong with that. Now I know it seems strange to you, but there's nothing wrong with this. All that's really important are changes in energy. So the initial energy is what? It's inescapable, 0. Now that may seem strange to you, but there's nothing wrong with that. Nothing wrong. Because the potential energy is always arbitrary to account. All that's important are changes in potential energy. That's all that's physically important. So there's, the potential energy is undefined to a constant. So instead of having mgh here, now we have initial potential energy of 0. But it's not going to make any difference, and we'll see. Let's look at that explicitly. Here it is. The initial energy is 0. No choice. What's the final energy? Now here's where Damon was saying there's some final kinetic energy. What's the final potential energy? Well, it's dropped at distance h, so it's minus mgh. So we got to put this here. We set these two things equal, and do you see what we get? We got equivalent to what we had before. Before we had mgh over here. Now we have minus mgh on the other side of the equation. So we're going to get the same answer, as we must. So it's just a matter of convenience what you want to choose the origin to be. If you do the problem correctly, it's not going to make any difference where you choose it. You just want to stick with it. Don't change it midstream. If you decide you want to change the origin because you see an easier way, you got to go back to the beginning of the problem. Oh, here's something else we can do here. Suppose there's an initial speed. So instead of this being v0, suppose there's some initial speed along the ramp here. Now how do we get the final velocity? Energy conservation, right? Whoops, I'm in trouble today. Okay, so what's the initial energy? I'm back to choosing the y equals 0 at the ground, okay? The initial energy is not purely potential. We have this initial kinetic energy. We set these two things equal, and we simplify, and we get this. And this will look very familiar to you. This is the no-time equation. But before we got it for a constant acceleration. We could only apply it to constant acceleration. Energy conservation tells us now that our solution was more general than we realized. You don't have to have a straight ramp. We have an arbitrary ramp here, right? As long as we can make it to the bottom. Okay, any questions about that?
Sir, can you scroll up back to the what's the easily determined conservation rate?
I can't hear you.
Up a little more, sir. On that U, is that mgy or is that mgh?
Well, h is the initial height. The potential energy at any point here, the potential energy is mgy. So you'll notice I didn't call this, similarly with the kinetic energy. In general, for the motion here, the kinetic and potential energies are changing, right? Energy is going from back and forth or from one to the other. So at any moment of time, this is the kinetic energy, that's the potential energy. Now I specialize to my initial and final points, and that's when I put in the h. That's a good point, okay? You know, I guess you got to learn. You learn this by doing it. You know, I mean, to me, it just seems so simple here. But I've been through this maybe too many times. So that's why we do problems, and we'll be doing them, a lot of them. This is going to opens up a lot of problems. We don't have to worry about doing constant acceleration anymore, right? So you know they're coming. You know all kinds of problems are coming. Any other questions? Now, this next demonstration, it's really appropriate not to do in class, but Gene and I have done a video. Right, Gene? So Gene's going to send me the link, a YouTube link.
Yeah, I can do that.
Okay. And then I will send it out to you, and I'm going to write it, I'm going to put it into the notes. Okay? And it doesn't last long. It's probably a 3-minute, 4.
It's been a while since I've looked at it.
Yeah. So I think you'll like it. The idea here is that it looks like there's a violation of conservation of energy, right? But you know enough now to think that when you look like you have a violation of conservation of energy, you're probably missing something. There's some source or sink of energy. You're not including all of these sources of energy or sinks of energy. And this is a case that we just kind of stumbled onto. The apparatus was built for another reason. So we made a video out of this, and I think it's good to watch it, yeah. And it's a little bit quantitative. We actually have to, yeah, you'll see. So I want you guys to watch that. And it's not long, right?
Wow.
God, I can't remember.
We always intend on not making it.
Yeah, it's a big problem with these science videos. I watched a guy, somebody sent out a few weeks ago to, Gene might have seen it, some UCLA young assistant professor at UCLA, and he was talking about different types of magnetism, and he was just racing through this thing. Did you see that one? Oh, it was obvious that he was told 3 minutes, that's all the public can, that's all they can handle. And he was just racing through it. I couldn't believe it. But so it is a problem. So we try to keep people's attention. We're learning. This is still a learning process. We've done a number of videos, but I don't think we've done enough yet to really know. We probably never will do enough to really know how to do it right. But we're getting better, I think, on the average. Okay, let's look at another. So I'll send that out. Let's look at another example here. We did this problem. From a Newtonian, from a work kinetic energy point of view. And I told you at the time that I felt uncomfortable with it. We had this, work done by the net force is the change in kinetic energy. Okay, so I got to find this work. And I told you that there's a much easier way to do it, and now we can do it. We're going to use energy conservation. Here's the idea. This block has some initial velocity. There's going to be a point at which the spring is maximally compressed. Right? For a moment, the spring will be maximally compressed. The instantaneous velocity will be 0 at that point, and we want to find that distance, the maximum distance the spring is compressed. That's the problem we did. And we did it from the work kinetic energy point of view. So what do we have here? First of all, energy is conserved. There's no friction. We've got a conservative force here, the force of the spring. So the initial energy has to equal the final energy. We're taking the final point to be right at the moment when it's maximally compressed. So in general, at every point of the path here, here's the kinetic energy, here's the potential energy. Now while this mass is moving here, what's the distance the spring is compressed? 0. This is going to be 0. But so it's still true, so comes in contact. We're assuming the mass of the spring is negligible. So the initial energy is this. It's all kinetic. The final energy is all potential in this case. We just set them equal and solve for x final. And this is the answer. We got 17 centimeters last time, I think. But conceptually much easier here than using the work kinetic energy theorem. Okay, any questions about that one?
That's to say that the spring is only compressed, it doesn't melt back. It just squishes.
Okay, yeah, this is what was worrying me. and that prompted me to say that we're neglecting, the spring has a negligible mass. What's bothering you is perhaps that the spring could bounce off the end here? Is that what was maybe I'm...
I just wanted to know if the spring is just squishing, it's not coming back. It's just
Oh no, it'll come back. It'll come back.
But
And
this
there's,
part that we've solved for is just for the spring compression.
it's the maximum compression. So it comes in, it slows up, and it travels a distance of 17 centimeters before coming momentarily at rest. And then it goes back, the spring pushes it back out. So in the end, the spring is back to its relaxed state. And there's no potential energy. That may bother some of you because you're thinking, well, isn't this going to oscillate or something? Yeah, but again, we're neglecting the mass of the spring. So this is an ideal spring. What's going to happen in that case is, because it has no inertia, it will just come back to being at rest at the end. It won't do that.
So I mean, using energy conservation, would that mass basically turn around and be going back at the same velocity in return?
Oh, that's a good question. Yeah, I didn't address that here. So what's going to be, now we're going to call the final state when it's back here. What's got to be true? It's got to have the same speed. It has to have the same kinetic energy. Neglecting losses, right? So it's going to have the same speed. It's just going to be in the opposite direction.
So then do we go to a point where we start talking about coefficient of friction and how that actually affects
We'll get
the
there.
energy?
We'll do that. I think that should be tomorrow. Now it's not a conservative force. So there's no potential energy. So how do we handle it? You'll see. It should be tomorrow. Let me see. Inclusion of non-conservative forces. It's tomorrow. So we'll talk about that. Okay, this is simple stuff, right? So let's make it a little bit more complicated. Now we have two conservative forces. We've got gravity involved here and this spring in general. But the total potential energy is just the sum of the individual potential energies. No problem. Okay, so the problem here is we're given that the spring is compressed 50 centimeters and the mass is released from rest. So the spring's going to push the mass out here. It's going to go up here and it's going to, we're going to assume that it makes it up to the top. So it has some final velocity at the top. Now, we don't know. It could go partially up this ramp and come back down. But it's actually safe here to assume that it's going to do it. If it doesn't, the math will tell us. You know, we'll end up with some imaginary velocity here. The math will tell us. It's got to. Okay, so we'll talk about that. We'll actually solve that. But for right now, let's just assume that it's going to make it up here, and we'll see that it does. Everything's consistent. You know, this may disappoint you, but many, scientists and engineers, I don't know about engineers, but many physicists, I can speak for physicists here, I think. When you're solving a problem like this, you say, wait a minute, how do we know if it's going to make it to the top or not? A lot of times we'll just make an assumption, and then if everything's consistent in the end, it's got to be right. It really has to be right. This may not sound logical to you, but it actually is. People do it. They do it all the time. We just want to solve problems as easily as possible, as transparently as possible. So if it can't make it up to the top here, don't worry. The math will tell us. And it's probably going to be an imaginary velocity is my guess. So that when you square it, you get negative kinetic energy. That's the only way it can conserve energy. Okay, so let's do it. What's the initial energy? It's it's the energy in the spring with the initial compression distance of 50 centimeters, converted to 0.50 meters. So we might as well compute this. This is one way of doing the problem. You can do it algebraically and come up with a formula at the end, but I'm just doing it a little bit differently here. I'm just going to go ahead and plug the numbers in, since we know this. So it's 62.5 joules of initial energy. What's the final energy? Well, we're going to have some kinetic energy. We don't know what that is. We're trying to find that velocity. And there's going to be some potential energy. What's the potential energy? mgh. That's the final potential energy. And we can calculate that, because we're given h, we know g, and m is 2 kilograms. Yeah. So let's go ahead and calculate that. So here's the initial energy. Here is the final energy. Look at how this has gone down. This is the initial energies. This energy here has gone from 62.5 joules to 58.8 joules. So what does that mean? Where is that energy gone? That's the way you want to think about this. Energy is conserved. It just can't appear and disappear. So energy's been transferred. That's going to be has to be the kinetic energy. We set these two things equal. This has to equal that plus there we go. Wow, I skipped a step here. The initial energy has to equal the final energy. So the difference here has precisely gone into the kinetic energy. That allows us to find our final velocity. And I get about 2 meters per second. Okay, any questions about that part? That's part of the problem here. Now we're going to ask, clearly if we don't compress this thing a sufficient amount, the mass is just going to go up. It's going to reach some maximum height, less than h, and then come back down. So, let's see here. In this case, it had enough to make it to the top and move along here. If we compress it a little bit, it's just going to come up and come back down. So where are we headed? We're headed, there's going to be a critical compression distance. What happens at that critical? That's the crossover between these two possible final states. One where it's moving along here, and one where it comes back down here. There's going to be a critical compression distance. And what happens at that critical compression distance? It comes up here, and it barely makes it to the top. So what's its final velocity? 0. That's right, think about it. It just barely makes it to the top. So now, we're going to resolve this problem. Okay, but now from a different perspective. Now we don't know the compression distance, but we're going to set the final velocity equal to 0. So that's the critical case. Here's the initial energy. We don't know. That's the C for critical here. We don't know that. The final energy, there's no kinetic energy, it's all potential. So again, we just use energy conservation, set them equal. This is, it's very simple. And we can find the critical distance. And this is maybe surprising to you. 48 centimeters. Why is that surprising? Remember the problem we just solved? I know it seemed like a long time ago, but it's just 2 centimeters less. Does that seem right? That's a pretty healthy velocity, 2 meters per second. And the difference, so I compress it 50 centimeters and it makes it up to the top and it's got some final velocity, some reasonable final velocity. If I do it a little less than 48 centimeters, it's not going to make it to the top, is it? Yep.
Is it because the K was so large, at 500 newtons per meter, that 2 centimeters will account for that?
Yeah, that's part of it. That's part of it. Another thing is, and I hadn't thought of that, to be honest with you. But another thing is, remember we have Hooke's law here. Right, the force of a spring, let me just do the magnitude. The force of a spring versus x, the magnitude here, is increasing. Okay? And we're out here somewhere. So we're talking, it seems like a small compression distance, 2 centimeters. But what kind of force do you have to exert to You know, we do it at 48 centimeters, it barely makes the top. We compress it 2 centimeters more and it makes it and has a pretty reasonable velocity. We've got to put work into that spring, and that's not a small work because the force is increasing linearly with distance. So even though we think this may seem like a small here, this value, the work that we're doing is not all that small because the force is climbing. And another reason is, you know, the steeper you make this, the greater that force is going to be, right? So I don't think this would be surprising to you if you had to cock this thing. You know, you did the 48 centimeters, and then you had to do that extra 2. You're going to find you have to put in a fair amount of energy, in some sense. Okay, I think any other questions or comments about that problem? Okay, here's one you've all solved, probably a number of years ago. The so-called loop-to-loop problem. So this has applications to roller coasters. So you have a roller coaster here that's released from rest. Frictionless track. It makes a loop. What's the minimum height so that it barely remains in contact with the track? Now, actually, for a roller coaster, it's going to remain in contact with the track because these amusement park people, they're going to protect their equipment. The public, they may not care much about the public, you know. So they will typically have wheels on top of a rail, and then what do they have? Wheels on the bottom. So no matter what happens here, the roller coaster, it's going to go, it may not have enough energy to make it up here, and it may come back down like that. Or it may actually come to rest at the top. So that's possible. That's possible. Or it may come around. The problem is the passengers, right? So we want to solve. We want to make this safe. We want to find the minimum H such that when the track goes around here, the normal force just goes to 0. So what does somebody feel sitting in the roller coaster? The person's upside down. You want to have a seatbelt on, but we want to, for safety, we want to design this such that even if somebody didn't have a seatbelt on or they hadn't properly put it on, that has happened. You know, I've noticed over the decades that like every 5 years, somebody dies at an amusement park. I don't know if you've noticed this. It's about time again, too, I think. I'm not sure. I haven't heard of one for a while. So, but, you know, we look at it.
Check out this video.
Yeah, okay. You know, there can be these catastrophes. So obviously you want to wear seatbelts here, but you may not have attached it properly, or it may have broken, you know, right? So we want to, yeah. Well, we have to, yeah.
We're going on a field trip.
You got me thinking. So here's the idea. We can focus, you know, you can think of this actually as a person. You don't want to think about it as the what's it called, roller coaster here. A person or something is sliding along here. We want the person or whatever, or the block here, just to remain in contact. So what's the normal force? This is a critical situation. If we release it up here, it's going to make the loop no problem. If we release it down here, what's going to happen? It's going to go up here, and then it's going to go into projectile motion. That's bad news for somebody in there. Okay? So there's a critical case that corresponds to it just going over the top, and the normal force will be 0 at the top. That's the essential physics that you need to recognize here. If I'm sitting in a seat, you know, I could feel fine here, and G is going to seem to be pointing this way from me. When I get up to the top, if there's a normal force on me, I'll think that there's, you know, that gravity is pointing that way. When the normal force goes to 0, what do I feel? I'm weightless. That's the critical situation. That's what we're going to solve for. And we'll do 2 demonstrations of this, believe it or not. This is a classic problem. And you've all solved it, or you've seen it, or you've solved it, or both. Does anybody remember when you were undergraduates? You don't want to remember? Okay, I don't know.
It's the same one we solved last lesson with the, on the end of the road. It's the same.
Yeah, I've forgotten, what were we doing there?
We were doing uniform circular motion, and you were talking about what happens at the top.
Oh, the vertical. Are you talking about this case? Yeah, it's similar. Yeah, the equations are going to be similar. Yeah, this is similar to that. So that's good. We're going to go over that again. So here's our force diagram at the top. In general, the person has some weight, and there's some normal force. We're going to set the normal force equal to 0. Here's Newton's second law. We have to use Newton's second law here, but we're going to, this is a multi-part problem. We got to do it, to solve this. We got to have information on the top here. The information, the critical information, is that the normal force will be 0. So here's F is equal to ma. We've got uniform, right at the top there's going to be uniform circular motion. So the acceleration is v squared over r. Remember that? We set the normal force equal to 0. That's the critical situation. So we get this. And it's best just to, so we get this condition. It's best, you might say, well, let's cancel the masses. It's actually better not to do that, and here's why. We're going to use an energy approach here to now solve for the rest of the problem. What's the kinetic energy at the top? Well, it's 1/2 mv squared at the top. And now we can put this in terms of something we know. Once we know this relationship, we can solve for mv squared and substitute it in here, and we get this. So this is something, r is something that's given to us. We're going to do, it's assume that we know r. We assume that. We don't have a specific value, but we're just, So we're doing this so that we can get the kinetic energy here. What's the initial energy? It's released from rest, so it's mgh. Right? That's the initial energy. And energy has to be conserved. So we set the initial energy equal to the final energy. We're calling this the final point. And we get one equation and one unknown. The energy at the top. There's kinetic energy at the top. That's this. And then there's potential energy. So we're calling this R0. What's the potential energy at the top? 2 mgr, because the height here is the diameter, 2r. There's a mistake in the notes here. Some of you probably already noticed this. There should be an r right here. This is not dimensionally correct. There should be an r. This is the potential energy at the top. This is the kinetic energy at the top that we got from Newton's second law. So we set the two energies equal, and we find that h is 5/2 r. So it's a fairly simple result, but it's hard to get your head around. The way I always think of it is, if h is 5/2 r, that means this is 1/2 r. Because this is 2r, and then I need 2.5, which is 5/2. So that right there, it's got to be released 1/2 the radius above the top. That's the best way to think of this. So it takes time to make this. I didn't make it just for this that you saw before. Well, we first with and without the rod. But can we use this here?
Sure.
Yeah. Yeah. That's the intent. And what do you think this black tape corresponds to? Take a wild guess. So this is going to go here. Here's the radius. If you have the radius and add it to this height here, you get that. Okay? I checked it several times. So the theory says that if I release it up here, what's going to happen? No problem. It used to slip nicely. Maybe this particular ball it used to be real nice and smooth. But up here, there's no problem going around the top, right? What if on the other hand, what if I release it significantly less than the critical case here? This is the predicted critical case. What's going to happen?
He'll come back.
I was waiting.
It gives them projectile motion.
So maybe that accounts for your killed person.
Yeah, accidents, yeah, fortunately, you know,
That doesn't need to be human.
the only damage was done is maybe a little indentation in the table. So that's why I stay in the laboratory, you know. Okay, so we have what's called a problem here. And I was okay, give me just a moment. I can't get this through. So anyway, oh, come on. It's a smaller diameter on the other end. Okay, so tomorrow what I'm going to show you first thing is we're going to release this from rest at the critical point. So remember, if it's down here, it doesn't make it to the top and it goes into projectile motion. Bad news, right, for a person, okay? So here you can actually see that it just sort of barely makes it. The string, typically the thread will go just slightly slack, and you'll see. I'll show you that tomorrow. And this was from the past. I shouldn't have trusted. I should have remade it. That was a mistake. Okay, so any questions? I'll show this first thing tomorrow.